What's up, guys? My name is the Knowledge Expert, and today we are going to work on some problems on electricity, specifically Kirchhoff's law, and a bit on Ohm's law. So let's start first with Ohm's law. So Ohm's law states that a difference in voltage, so voltage, or difference in potential, is equal to I, which is current, times resistance. Resistance is measured in ohms, current is measured in amps, and voltage, well, is actually measured in volts. So you can imagine voltage as the thing pushing a charge to flow in a circuit. If you have a circuit in which current flows, basically you have current that flows from the positive terminal to negative. Current is not negative. Conventional current is not negative charges flowing, but it's actually positive charges flowing from the positive terminal, which is the big one, plus, to the negative terminal. And so you have this. Voltage is really the thing pushing. It's a difference in potential energy, and it's pushing in a sort the current, and resistance is something resisting really the flow of current. So this is Ohm's law. You could also write it in multiple ways. You could have delta V over R, which is equal to current. You could also have the resistance, which is equal to delta V over I. So you could rewrite Ohm's law in many ways, and this will be pretty important. Now let's make some circuits. Let's make some serious circuits. Let's say we have a battery here, a source, and then you can have two types of sort of circuit that has. Let's say you have something like let's say you have something like this. You have a resistance here, a resistance here, and it goes just like this. And so we know that current will flow like this throughout the circuit. This is called, but the resistors, as you can see, the resistors and the current flows in something we called a series circuit. So this is a series circuit because the resistance, basically the current has nowhere else to go besides here, right? It follows in series, right? You go here and then you go here. You could also see series circuit like this in a way. If you have we're trying again. You have something like you have a resistor here, and then you keep having a resistor, and then these are in series because they follow one another. So this is a series circuit that goes like this. And this is important because to know a series circuit, the total resistance of a series circuit, let's say this is R1 and this is R2, the total resistance will be R1 plus R2 plus etc. Let's say R3 and then R4. So this is a series circuit. However, you could also have something called a parallel circuit. Let's say you have this same source, and then you have here R1, a resistor, but then you still have another resistor here. Now, this is not in series anymore, where current will flow like this easily, right? Because now, in a way, the current has multiple paths to take. Just follow the current, right? If you go here, now the current it could either go by here or it could go by there, right? Because it needs to go back here to the negative terminal. So the current can go like this, or it can go like this. So that means that this is a parallel circuit. You could also see that it's evidently in parallel, right? So you could see that these two resistors are parallel to one another, but they must be connected to the same point. So something, it's not always parallel if it visually looks parallel. If, for example, you have a a source here, and then you can have something like, you could have a resistor here, but then that is connected to something else, whereas you'll have something that is parallel, but then it'll be connected to something, to another sort of circuit, if you will. Let's say you have something like this. This is not parallel. This is not parallel because they're not connected at the same endpoint. So you do want for it to be connected at the same endpoint. Now this is a joint, and this will be pretty important because in a parallel circuit, you can identify evidently some joints, because this is this is not a joint. No, this is not a joint. This is a joint because circuit goes here. You have a joint here. So parallel circuits have joints. Now, as we found the formula for a series circuit, which the total resistance was R1 plus R2 plus etc. In a parallel circuit, it's 1 over R total, which is equal to 1 over R1 plus 1 over R2 plus 1 over etc. So these are the formulas for both a series circuit and a parallel circuit. Now let's do some exercises. Let's do a bit of exercises to see if we know. So, alright. So let's say we have a 9-volt battery here, which is connected like this, 8 ohms, and then 4 ohms, like this. This is a circuit we have. So what will be the total resistance? So you could pause the video and you could solve for yourself. But here what you do is that you can clearly see that this is a series circuit. And as we remember, the total resistance will be equal to R1 plus R2. In this case, R1 will be 8 ohms and R2 will be 4 ohms. So it will be 8 plus 4, which is equal to 12 ohms. So you could rewrite this like this. This is the equivalent. This is, you could write the equivalent. So the resistance is the equivalent resistance of the circuit, right? The total resistance is the same thing as the equivalent resistance. And so it is the equivalent of writing it like this, of 12 ohms here with the 9 volts here. Now let's say you want to calculate what the current is. Now evidently there is only one current passing through here. So the current, also you should know that when you do in a series circuit, the current will be equal. So the current in a series circuit is the same. This is the same current that passes through. It won't have a different current as, for example, as a parallel circuit, which will have a different current. If you have, say, something like this, a parallel circuit, the current passing here will not be equal to the current like this. So let's say I1 here and I2. I1 will not be equal to I2, but the voltage will be equal here. Voltage of the battery here will be equal to the voltage here to the voltage of this resistor. So because we do have the same current, all we could do is that we could use Ohm's law, which we remember is V is equal to IR. So we could just rearrange and get I, which is equal to V over R, which will just be 9 divided by 12, and we will simply get 3/4 amp. So this is the final answer. If you want to know everything you want to know about this circuit, well, now you know. You know the current that passes through. You know the difference in potential, right? The voltage, which is the difference of potential of this point and this point, in which case this is 9 volt and this is 0 volt, and so the difference of potential makes the source here, which is 9 volts. So you know the voltage. You know the resistance here of the resistor, and you know the current passing through. All right. Let's do another problem of equivalent resistance, or total resistance of a circuit. So let's try this one. We have a source here, and then we will get, so this is also 9 volts. Let's put 9 volts here. And then we have 8 ohms here, and 4 ohms here. So let's calculate everything we need to know about the circuit. So, firstly, let's calculate the current, because the thing missing here is the current, and we could use Ohm's law to know what the current is. So the voltage, we know that the difference in potential, which is the voltage here, is 9 volts. And because this is a parallel circuit, this is also 9 volts. So this part here is 9 volts. But also this part here, the voltage is 9 volts across the circuit. However, pay attention and be careful here, because the circuit is not the same, the current is not the same here. You have current here, which let's call I1, which is not the same as I2 here. So I1 will not be equal to I2 in this situation. So that means that you'll have to do two different things. So firstly, let's get Ohm's law back. And if you remember, Ohm's law was V, which is equal to IR. And we want the I here, so I will just be equal to V over R. And so let's calculate the current here. We'll take the voltage here divided by the resistance here, and then we'll take here, which is the voltage here, V, divided by the resistance here. So for I1, this will be for I1, and this will be for I2. I1 will be equal to 9 divided by 8 amps. And for I2, we'll get also voltage divided by R, but the R is different, which will be 9 divided by 4. So 9/4 amps. So that is the answer for our circuit here. And of course, if you want to add the two currents or the two resistors, so we did found what the current is, but in that problem we had a 9 volt here, and then we had 8 ohms and then 4 ohms. We did not calculate the equivalent resistor, so let's go back here and try to find the equivalent resistor here. So this is a parallel circuit, so it'll be 1 over R total, which is equal to 1 over R1 plus 1 over R2. So therefore 1 over R total will be equal to 1 over, or no, more like R total or R equivalent will be equal to 1 over 8 plus 1 over 4. So if we take our calculator and we do 1 divided by 8 plus 1/4, and then that at the exponent of -1, this will be around 2.66 ohms. So that means that you could rewrite this circuit as like this. Notice that despite this being a parallel circuit, when you get the equivalent resistance, right? When you get the total resistance here, this becomes a series circuit, you see? So that means that if you want to calculate the I, here it is the same, right? Because this becomes a series circuit. So here the laws of the series circuit will apply. But there's only one equivalent resistance, so there's no other resistance I could calculate. But this becomes a series circuit. So this was parallel circuit, and you transformed it using the equivalent resistance to transform it into this. And so you could verify, if you want, if the I is good. If we remember, so if you have V divided by VIR, and then you want to know what the I is, you'll have V divided by R, which will be 9 divided by 2.66. 9 divided by 2.6, yeah, till infinity. And we get 3.375. So the I of this circuit will be 3.375 amperes. All right. So that's how you do it. Now let's go on to something new, which is Kirchhoff's law. Kirchhoff's law, or Kirchhoff's laws, actually, because there's two rules, if you will. So the first law of Kirchhoff is Kirchhoff's current law. So the way the current law works is that, when we saw something, we saw a junction, we saw a joint in a circuit. We have a source here, and then let's say you have something like this, and then you have something like this, and we saw a joint here. And what happened is that, well, this is important because you have current passing here, and the current can escape and go out here, or it could go out here, right? So you have a specific I1 entering, you have an I2 escaping right there, and you have an I3 escaping here. So essentially what the current law says is that the sum of I of the current that's entering is equal to the sum of the current that's escaping, which is that's escaping, I guess. What do you write? Yeah, the sum of the current that gets out. Yeah, let's go out. So the sum of the current entering is equal to the sum of the current that's out, which you could also write, I suppose, as the sum of current entering minus the sum of current out is equal to 0. So this goes to anything. If you have any junction or a joint here, and you have current going here and current going there, and you have current escaping here and current escaping there, and you have this and this, let's call this I1, I2, I3, I4, I5, and I6. So this will just be I1. So let's see all the all the current entering. So I1 is entering, plus I2 is entering right here, this ugly arrow. Okay. I2 is this, plus I3, and then we see, right? We see that I4 is escaping, it's out, so it's going to be negative. And then we're going to add I5 and I6, which will be equal to 0. So that is Kirchhoff's current law. And his second law, Kirchhoff's second law, is the voltage law. And basically what the voltage law says is that in any sort of loop that you have, so I think you could also call it, I think some people call it Kirchhoff's loop law. So in any loop that you have, let's say you have this sort of circuit right here, let's um do a thing here, and then you have some sort of thing here, just like that. Essentially, what it says is that the voltage, the sum of all the voltage here, or the sum of all the voltage in this entire circuit is equal to 0. So that means that if you want to know here, so the type of problem you can have is that you'll have some current going here. So of course the current will be the same around because this is a series circuit. So you'll have the current going around here. And what you'll do is that you'll have the voltage here. So you have a voltage here, which is just V, or you could write it, some people write it epsilon, because epsilon, I suppose, is at the source, which is the voltage. And then you can have here, you have a resistance, right? But there's current flowing through it, and according to Ohm's law, I times R is equal to V, and here you have I times R. So this will be negative I times R minus I times R is equal to 0. So why? Because so you add these up, but this is actually negative, right? So you're supposed to add these up, but because these are negative, this is minus IR. Because IR, don't forget, V is equal to IR according to Ohm law. All right. And so you have these, and this could help you to find the current in a specific sort of circuit. So if you have this, so let's take this, and let's take an example and give a concrete example. Let's say you have 12 volts here. This is 3 ohms, and this will be 6 ohms. And then we want to know what the current is in the circuit. All you have to do is 12, right? Because to know how you do it, you need to have a hypothesis. So you're saying that you go, let's note our sort of joints here, or not joints, but like these edges. And so you have A, B, C, D, and we'll say that we think our hypothesis is that it goes like this. So we're saying basically that the current will go through A, B, C, D. This is like how we hypothesize that the current will travel. And when you have this is important. So this is negative and this is positive in a so we already know that this is positive and this is negative. When you have a current going from negative to positive, that is positive. So when you have the current going like this in your hypothesis, you consider it positive. So when you say that you say the current goes like this, and so it goes through the battery in negative to positive, then that current, then the voltage you'll say will be positive. You'll consider the voltage positive in Kirchhoff's voltage law. However, when you have a current going like this in a resistor, so the current actually goes like this, and you said that it's going like this, the current is going like this. So if the current goes in the same direction as your hypothesis, then it's actually negative, because the current, when it goes in a resistor, the whole idea of a resistance is to resist the flow of electrons, right? You must imagine all this a circuit like water flowing, right? Current is water flowing, and a resistor is like the pipe getting smaller, or having a smaller diameter, making it harder for it to flow, simply. Whereas the voltage, the source, is like pushing the water. It's like a pump. And so it's normal that in a resistance, it will be negative voltage, and here will be positive. So let's solve this problem here. So we have plus 12 volts minus the voltage here of R1, the voltage of R1 here, which according to Ohm's law will be R times I minus 6I, because we have a series, the I is the same, will be equal to 0. So if we have minus 3 minus 6, we have minus 9I here. So 12 minus 9I is equal to 0. So 12 is equal to 9I. We put the there, and then we divide by 9, and then you get your current. And the current is 4/3. I is equal to 4/3 amp. And so that's how you do a voltage law problem for Kirchhoff. That's how you deal with Kirchhoff's voltage law. So let's do another problem here. We'll work with Kirchhoff's voltage law a bit more. So we say that our edges here will be A, B, C, and D. And then we have a battery here, a potential, right? A battery which creates a difference in potential of 5 volts. Goes to the battery like this. We have a resistor of 8 ohms. Goes to C. Now we have a battery of 17 volts. And finally, we have, or not finally, but we have 4 ohms here. This goes to D. And then you have another battery of 12 volts, just like that. And so, our hypothesis, where we're going to say that the current goes, will be in ABCD. So we're going to say that the current goes like this. So if you get a negative value at the end, let's say if I will be equal to negative, I don't know, X, and you said that the current goes like this, well, that means that the current will go the opposite way. So if your hypothesis is wrong, if what you did is wrong, where you thought the current gets negative, then it's the other way. So we'll apply Kirchhoff's so in this circuit ABCD, in this loop ABCD, we'll take the sum of the voltage is equal to 0. And so let's start. Let's follow our little electrons, how their little adventures. All right, so they go like this. So this will be positive 5 volts, right? Because it goes, as I said, it goes negative, positive, and then it goes 5, so plus 5, right? Because it goes like this. Then it's minus 8 times I. Of course, again, this is a series circuit, so the current will be the same in this circuit, so you only have to find one current. All right, here you'll do minus 17 because before you had minus to plus, but here you're going plus to minus, so evidently you'll have you have a negative value of 17. And then minus 4I, because again, this is the ohms voltage law for both, right? So you have V is equal to IR, and we're simply trying to find the voltage here, so doing IR. Minus IR, and then minus 12 again, because you're going plus to minus, which is equal to 0. So when you're gonna do this, now let's do this. Minus 8 minus 4, we have negative 12, so you have 5 minus 12 I, minus 17 and minus 12 is equal to 0. You have 5 minus 17 minus 12, which would give negative 24. So you have minus 12I minus 24 is equal to 0. So you'll have negative 12I, which is equal to 24. And then you'll just divide like this. And so I gives you negative 2 amperes. Notice we have a negative sign, so that means the current does not pass like this. The current does not pass as I showed. The hypothesis was wrong. So the answer is that the current passes like this. It doesn't pass A, B, C, D, A, but perhaps it goes D, C, B, A. And so our I will be equal to 2 amperes in that direction. Now let's do another problem on Kirchhoff's voltage law. All right, this is going to be a bit tricky, but you can do it. So we'll have a circuit. Again, we'll put the edges here of our little square here. We have A, B, C, and D. And then we'll have our first sort of voltage here, our source, which, as I said, you could put it as epsilon 1 if you want, which will be 12 volts. And then, like this, and then you'll have a resistor of 1 ohm. So you have a resistor of 1 ohm. It goes to C. And then you have a resistor of R2, which we know R2 to be, you actually don't know R2 in this situation. Equal. And then you go to D, and then you have your battery here of epsilon 2, so you have your second battery, which here is given to be 5 volts. It goes to A just like that. Just like magic. Wait, hold up. Actually, do know R2 to be 2 ohms. Never, my bad. And then you actually, yeah, you know everything, I would say. And then you have diagonal here 9 ohms, just like this. So this is a pretty tricky one because, as you can see, Kirchhoff's law says that Kirchhoff's voltage law says that in a loop, in a sort of loop circuit, your voltage will be equal to 0. The sum of your voltages will be 0. But here you don't have 1. You can consider 1, which is A, B, C, D, right? But you can also see that A, B, C, A is in itself a loop. This could be a loop. You could consider A, C, D, A to be a loop. So you'll have to watch out for that, because a loop is not necessarily just a circuit, but it depends on where the current can go. The current can go like this, as it can go like this, as it can go like this. So you must really draw, I would say, the current, so you can understand a bit how the electrons move, what paths they could take, and watch out in your calculations as always. So the first thing that we'll do is that we'll use something we didn't use in a long time, right? It's ancient almost. It's Kirchhoff's current law. You guys remember this? Current law. So we do see that there can be a sort of current law here, because our goal here is to calculate the current. But remember that this is not necessarily just one series circuit, because you can't just go here, right? So the current doesn't just have one path. It can have multiple paths. It could go by here, or it could go by here. So already you'll have sort of three current. So let me label them in multiple colors. So the colors we'll have for this will be, let's say we have this. We have current flowing here. So my so yeah, we'll have current flowing here for let's call it I3, I suppose. This is for, so of course this color will be for ACD, A loop. You have a yellow, let's take a nice little yellow of this circuit flowing like this, which I'll call I1. And we'll have a orange one like this escaping, which we'll call I2. So I2 only goes here. This is the only part I2 goes on. The rest, yellow goes like this, I1 goes like this, and I3 goes like this. All right. So here we have our three currents, and don't forget that when we have this is why I talked about Kirchhoff's current law, because as you can see, we have one current, I1, is entering, and you have two escaping. So if you remember, it's going to be the sum of the current entering will be equal to the sum of the current out, escaping. And so you could also write it as the sum of the current entering minus the sum of the current escaping will be equal to 0. And so as you can see, I1 is entering minus you have 2 escaping, I2 plus I3. Right? So you'll have I1 minus I2 minus I3 is equal to 0. So that's for the current law. So now let's start back to Kirchhoff's voltage law and do some ABCA. So this will be our first loop that we'll work on, just like this. The current will go like this. So notice that we'll have I1 going like this, and then we'll have I3 going like that. So we'll just follow the current, and we'll go yellow and then sign. So we'll go where we'll change color, I suppose, when one gonna go. So current goes first like this, or maybe let me go yellow here. So current goes like this. So that means we'll go 12 volts because we go like this. So it's positive 12 because we go negative plus. So it goes 12 volts. Plus 12 volts. Then, because our hypothesis is ABCA, so this is our hypothesis that the current's going to go. Next up, we have 1 ohm. So it's going to be minus 1I. I'm going to have minus 1I. I1, of course, because we're working with I1 here. And then finally, we'll no, wait, never mind. So we're not going A, B, C, D. So it's going A, B, C, A. It's going like this. This is how the current goes. So you should remember that when we're working right now with A, B, C, A. So this is how the current goes. So we're gonna work with yellow and orange, not sign. So forget this for now. So we go A, and then it goes 12 volts, which is positive because it goes from negative to a positive terminal. Then it goes to a resistor, which is negative, so negative 1I1. And then it escapes here, so it will be negative, because we have a resistor here, negative 9. I2 is equal to 0. Next up, we'll do ACDA. So this is our first formula to calculate I1 and I2. Next up, we'll do ACDA. We'll try to find some formulas and maybe try to do some equations and try to find the answer. So follow the current, ACDA. So it goes like this. So we'll work with orange here. So our hypothesis is that it goes like this, but it goes in the opposite way. That means that it's going to be positive here. So we'll have, so in ACDA, we'll have minus 9, or no, this will be 9 I2, and then we go like, and then like this, now we're at sign. So we did orange, and as we saw, our hypothesis is in the opposite direction as orange in a resistor, so it's positive now, positive 9 I2, minus 2 I3, because it goes in the same direction as I3, and then this will be negative 5, because it goes from positive to negative. And so this is our second equation. You could also rearrange the terms if you want. You can maybe have minus 5 minus 2i3 plus 9i2 is equal to 0. And so you already have for this and for this. And so you already have the two equations you need to find the current. Because now that you have these two equations, you can now plug in, you can now isolate one of them and you could plug it in the other one. So let's try to, here in this equation, if we want to isolate I2, let's say, we'll have minus 5 minus 2i3 is equal to negative I2. And so I2 will be equal to I3, I guess. Well, we to do this problem, you must have the same variables in one part and another. So in this case, let's try to, what if we isolate I3? So we'll have minus 5 plus 9i2, which is equal to 2i3 divided by 2 divided by 2. And then you have minus 5 plus 9i2 divided by 2 is equal to I3. And so you already have an I2 in here. So 12 minus 1i1 minus 9i2 divided by 0. I guess you could, yeah. So wait. We could just no, we're not gonna do that. We're gonna rewrite this one as minus 5 minus 2 times I3, which is negative 5 plus 9i2 divided by 2 plus 9i2 is equal to 0. So we just have I2 here. And so if we do that, let's multiply here. So I have minus 5, and then we have minus 2 times minus 5, which would be 10. So I guess it'll be, or maybe we can have like minus and then 2 times 5, which is negative 10. And then plus 2 times 9, which is 18i2. And this will be divided by 2, so I will simplify, of course. Plus 9i2, which is equal to 0. These will simplify, and it'll be minus 5 minus negative 5 plus 9. I guess we just came back where we began. Plus 9i2 is equal to 0. And then we'll just distribute the minus now. So we'll have plus 5 minus 9i2 plus 9i2 is equal to 0. So this will just cancel out, and then I guess these cancel out, so it gives us 0 as we wanted here. But to calculate these, you'll have to do a system of equation. I just did it so I could verify if it equals a 0, and as you can see, it gives us 0 really well by just replacing the I2 and the I3 by writing I3 as the current 2. But I just wanted to verify if it gives 0, and we obviously get 0, so our calculations were correct in the two equations. So to find the I2, I3, and I4, to find the current, you have to do a systems of equation. And so you'll get I1 is equal to, the current will be equal to 3A, I2 will be equal to negative 2A, and I2 will be equal to 1A, 1 ampere, and I3 will be equal to negative 2 amperes. So I'm not going to do the calculations now of the systems of equation, but you'll have these three equations that you could use to calculate the current of these three. If you want, you can do it. That's about it, guys. That's about Kirchhoff's laws and Ohm's law and parallel and series circuits. So that was on electricity. That's about it, guys. See you.